Yes, sir,
Um,
you are audible.
okay, so I would like to briefly say what is storm surges and how it is being affected for all our Indian coast. We have a very long coastline, about 7,500 kilometers, and most of the coastline is being affected every year, by the cyclones, thereby storm surges. So therefore, I would say something about storm surges and tropical cyclones, how these storm surges can be modeled through finite difference and finite volume models. So I would briefly touch upon that. And let me begin with what is storm surges. Most of the participants may be knowing about the storm surges. It's a kind of wave. I would say that a kind of wave, particularly it's a long wave. I will explain what is a long wave and all, because many participants may not be knowing the details actually of the short waves and long waves. I will explain a little bit more also to that, so that you all can understand what is that difference between the short waves and long waves. But let me start with wave. You all know that a wave is an oscillating disturbance which spreads through any medium, is called a wave. This is a very basic elementary, definition of a wave. But you have only two types of waves, whether you consider in oceans or atmosphere. That is transverse waves and longitudinal waves. And if you again specifically in the transverse waves, the definition of these transverse waves, you all know, most of you, the particles of the medium no move to and fro at right angles to the direction of the wave propagation. So, and then you all know that what are the transverse waves, ripples in a pond. That's the best example which we learned actually in the in the school actually. Okay, there is another wave, that is longitudinal wave. In longitudinal waves, the particles of the medium, move back and forth in the direction of the wave motion. Best example is sound waves. Okay, so these are the only waves which actually we are interested in oceans or atmosphere. Okay, again in transverse waves there are two kinds of, because it's in right angles, so to the direction of the wave traveling. So therefore you can see from the next slide, this is actually transverse waves. These are actually vertical transverse waves, and these are the horizontally transverse waves. Both are actually transverse wave. One is moving actually right angles to the direction of the propagation. Here also in the horizontal direction, this one. But both are at the right angles to the direction of the propagation of the wave. So, but this is very, very, dangerous. And particularly this storm surges, tides, tsunami waves, are actually all those waves come under this vertically transverse waves. And horizontally transverse waves are not harmful much. Okay, so compared to this one. So therefore, our category of storm surges fall under this one, vertical transverse waves. This is very, very important. And another one is actually longitudinal waves. Best thing is the pressure, compressive wave, compression and all these things will. This is sound waves actually. Basically, the sound waves are created by these longitudinal waves. Therefore, this we are not interested in, because that's not our discussion. What we are actually discussing is that vertically transverse waves. Okay, if you look at frequency spectrum of the waves, different waves, starting from the acoustic waves, we are not interested in this one. Capillary waves, the main restoring force is actually tension, surface tension is this one. So we are not interested. And from other waves, actually beyond capillary waves, they are called gravity waves, starting from the sea waves to planetary waves. They are all actually under gravity, because gravity is the restoring force. There are two kinds of waves, short waves and long waves within these gravity waves. Short waves means the wavelength is small compared to the wave height. Okay, so that's the fundamental difference between it. And long waves means the wavelength is very, very large compared to the wave height. So therefore, you can always consider wind waves are short waves, and rest of the waves are actually come under long waves. For example, storm surges, tsunamis, tides, all those other type of planetary waves come under this one. Okay, therefore, we are discussing mainly long waves, not short waves. Okay, so if you look at the energy related to each wave, you can see the wind waves, short waves have got very large, energy stored here. For example, swells, wind waves, of course, swells is again a long wave. Wind waves particularly, they are actually short waves, but both are having very large uh, um, energy stored in that one. And after that, again, you have different kind of waves, so storm surges, tsunamis, and after that you have tidal waves. So tidal waves has got large energy, it is having actual large energy. So that's why tidal energy can be extracted in efficient manner if it is using the proper technology. Okay, but what I'm interested is actually storm surges, whose time period is about 20 minutes to 1 hour, something like that, a time period. So tsunamis is also having about 1 hour to 2 hours, something like that. Okay, this is about the time period of the storm surges. And another interesting thing is that you have so many, as I said, we have a very long coastline, about 7,500 kilometers, Indian coastline, and you have so many kinds of hazards, coastal hazards. Okay, for example, cyclones, storms such as tsunamis. I have listed out all kinds of hazards, including, sea level rise. There are some algal blooms. This is also a kind of this one dangerous coastal currents, rip currents, and all. Many of you may be knowing some of these, but I'm not working actually in all these areas. My of areas interested to related to cyclones, storms such as tsunamis, and also sea level rise and tides. These are the areas in which I have been working. So I would like to concentrate within these topics. And how do you say that coastal protection in India is a very, very effective way? Okay, so you can always say whatever you spend for the coastal protection in India is really very economically feasible for an Indian context. How do you say that one? So I will just show that it's very because we have a very, so many coastal people are there near. I think it is about 40% of the Indian population live in the coastal regions. So it is very important for any government to protect actually our coastal regions. Okay, but is it economically feasible or not? How do you say that one? So you can always say that it is economically feasible on two conditions, which I would like to show you. The first one is that if you look at this histogram, this is the population. This is the population per kilometer of the coastal defense. Okay, India, Japan, Netherlands, USA, Australia, Canada. I have taken some, countries where population per kilometer of coastal defense. If you look at this histogram, India is actually placed in the first. Okay, what does it mean? What does it mean? That means the population living in per kilometer in India is about 170 compared to other countries. So India is actually, that means it's very important if you spend any amount of money for the coastal protection, so it will be benefited by to the many people in the country. That's very important. So this is the first criteria for the feasibility, economical feasibility of coastal protection. And another one, if you look at this is something kilometer per 1,000 kilometers. Okay, comparison of the coastal length per land area. We have actually coastal area versus the total area. That's what it gives actually. Okay. For example, if you look at this one, Japan is actually, they don't have much inland area. Okay, they have actually most of the thing is actually coastal only. So 91.3, terms in terms of area is about 91. You can say in terms of percentage, but India is actually the last. Okay, so that means, what does it mean? That means compared to inland area, our coastal area is very, very small. That means if you spend money, if you spend any amount of money, 1 rupee, let us say 100 rupees, okay, so it will be benefited to the coastal region in more effective manner. Okay, this is called actually cost benefit ratio, if somebody knows about that one. So that means if you spend little amount of money, it will be benefited to the larger population in Indian context. Okay, so this is just now I will come back to what is a tropical cyclone. Most of you, some of you, the participants may be those who are living in the particularly in the coastal regions, they might have experienced a cyclone crossing the region. Okay, so you all know that actually it is a large atmospheric vortex which forms over tropical warm oceans. A severe cyclone can extend horizontally from 150 kilometers to 1200. That is the area wise. I am talking the horizontal length scale. It will go up to 1200 kilometers with fierce winds spiraling around a central low pressure area. In the northern hemisphere, the air rotates around the cyclone in an anti-clockwise direction. So, which is shown here. Okay, the winds are actually moving anti-clockwise direction. Okay, this is the direction of the wind in the cyclonic winds actually in the northern hemisphere. But in the southern hemisphere, it is exactly opposite. Okay, so this is the kind of large vortex which takes place in the tropical cyclone. Okay, but if you look at this any tropical cyclone from the satellite, this looks like this. Okay, these are the this is the eye of the cyclone. This is the eye of the cyclone, and surrounded by strong cloud bands. These are the cloud bands. Okay, very thick cloud bands during the cyclone time. So okay, so here this is the center of the cyclone, means there are no winds at all, and there is a clear, you can see the sky very clearly in this very small. The radius of this eye of the cyclone is about 5 kilometers to 10 kilometers maximum. Okay, you can't get this one. And that means within that region, within that circle, okay, you can see the sun very clearly. You don't know as if you are actually passing through a cyclone, because it's absolutely clear, cloud free. Okay, and no rain at all. Okay, and no winds, absolutely calm winds will be there, as if you are not surrounded by a cyclone. But this is all actually, it's a dynamic storm. So that means after 1 hour, with the speed of the cyclone, okay, again, this eye of the cyclone, the position of the eye of the cyclone changes. Okay, so therefore, again, you will be, you will be affected by the cyclone actually. Okay, so this is what is very important. What is the width of this eye of the cyclone? Where exactly the winds are very, very strong? This is called radius of maximum winds. Wherever the radius in which the winds are very, very strong, that's very important actually for our simulations also. Okay, and also in this region, in the next slide, I will show you the typical cross section of the cyclone. If you look at this one, this is the pressure. Okay, the pressure at the eye of this one decreases. Okay, that is the minimum low pressure is recorded at the center of the cyclone. Okay? And as you go away from the center of the cyclone, again the pressure increases and it comes to normal. So this is a typical profile of pressure field versus actually this one wind speed also. Wind speed is also given. So you will get actually maximum winds. The maximum winds are actually coming at a particular distance from the eye of the cyclone. This is called radius of the maximum winds. Okay, this is called radius. This is of course diameter, but if you make it half of that one, you can say that it is radius of maximum winds. Roughly, the radius of maximum winds will be about 30 to 50 kilometers. That is for any cyclone. And the pressure drop is associated about, depends upon the intensity of the cyclone. It may, anything more than 17 millibar pressure drop, you call it is a cyclone. If it is more than that one, you call it actually uh, a severe cyclone. So it depends upon the how much pressure drop is there. So accordingly, the category of the cyclone is actually named. So this is the way. That means what you have to understand is that the intensity of the cyclone is mostly determined by the how much amount of pressure drop is there. Okay, if the amount of pressure drop is more, the winds associated with the cyclone are also very strong. So these are all two related. Okay, so therefore, if I say that the pressure drop is more, that means you can assume that the winds associated with that one is very strong. That means intensity of the cyclone can be determined by either pressure drop or the amount of winds associated with that cyclone. So this is the way you can categorize any cyclone. Okay, now if you, this is very interesting statistics. Okay, this is the return period for a particular time period. For example, if I calculate return period for every 10 years, 50 years, 100 years, okay, for each maritime states, we have got 4 maritime states along the east coast of India, and there are 4 maritime states along the west coast of India. Okay, but mostly the cyclones are actually, you know, confined to along the west coast, Maharashtra and Gujarat. And along the east coast, all the maritime states are actually facing the tropical cyclones. Okay. Nevertheless, we have seen actually there are some cyclones for Kerala and Karnataka. So very rarely you will see that one. Okay. So if you look at actually, if you take the more than 125 years data is available at India Meteorological Department, how many cyclones for each state and each district is actually having. Okay, so if I take all that statistics and if I calculate the return period means some of you people may not be knowing what is return period. But in 10 years period, what is kind of actually tropical cyclones hit in a particular region? That gives actually return period. Similarly, in 50 years, you know, what type of intensity of cyclones are crossing that particular region. Similarly, 100 years. So this gives actually a kind of understanding what kind of cyclones in 100 years period. So naturally, in 100 years period, you can expect very severe cyclones. For example, 1999 we had a super cyclone crossing around that Puri, Pardeep, Mahanadi basin in Odisha. So that comes, super cyclones cannot be on 10 years scale. It will be about 100 years. So you will get actually this kind of cyclones once in 100 years. So that is the, that's the way you have to look at about the return period. So if you look at, for example, Kerala, Karnataka, Maharashtra, Gujarat, as I said, Kerala, Karnataka, this is the pressure drop. Pressure drop, as I said, in millibar, units are in millibar. If it is a small, then you can say that the cyclone is not very intense. Okay, if it is more, then cyclone is more intense. So you can see that for 10 years, 50 years, and 100 years, for Gujarat and Maharashtra, having, on different time periods, having larger pressure drops compared to Kerala and Karnataka. And again, if you compare Maharashtra and Gujarat, Gujarat is the most vulnerable for the, having more number of cyclones with a larger intensity. Okay. So here it is on 10 years period, you have a cyclone of 12 millibar, on 50 years, 40 millibar, on 100 years, 66 millibar. So there is actually cyclone, Veeraval cyclone in 19, if I remember correct, that was in 1982 or 83. There was a Veeraval cyclone, had actually very strong, cyclone, very severe cyclone, having actually pressure drop of 66 millibar. So you will get actually once in 100 years a kind of very severe super cyclone or severe cyclones, you will get it. That is for the west coast of India. Similarly, you have actually, 4 maritime states along the east coast: West Bengal, Odisha, Andhra Pradesh, Tamil Nadu. But if you consider West Bengal and Tamil Nadu, the return periods are, the pressure drops associated with any return period is small compared to the pressure drops for Odisha and Andhra Pradesh. So that means you expect that Odisha and Andhra Pradesh are actually having, are usually getting higher intensity cyclones compared to West Bengal and Tamil Nadu. And again, if you compare Odisha and Andhra Pradesh, this Odisha is gets more severe cyclones compared to Andhra Pradesh also. So therefore, this gives a overall picture how each Indian maritime state is actually affected by cyclones and what intensity. Okay, this is actually a kind of return period analysis. This gives actually a kind of perspective of about cyclones, how intense it is for each maritime state. Okay, very important thing is that why some cyclones cause more havoc compared to any other cyclones. It depends upon the many factors. One factor is very important is that continental shelf. How do you define continental shelf? Some people may not be knowing. This is the beach, for let us say, okay, and this is the typical bottom profile of the ocean. That means as you go away from the beach, the depth of the ocean increases. Everybody knows that one. But up to some distance, the slope of the depth, varying, depth increases, but it varies very slowly. Okay, so there is actually 1 kilometer distance in 2 meters depth actually. Okay, in 1 kilometer distance, there is a change in the depth about 2 meters. That is called continental shelf. Okay, and there is after that the depth increases suddenly. That means in 1 kilometer, 70 meters depth increases. Okay, so like that, this is a typical profile. But at any coastal place, the length, this is called width of the continental shelf from beach to up to the where the shelf break comes. Okay, that is called continental shelf. Okay, because this width of the continental shelf is very, very important for the storm surge amplification. Okay, that means the surge height increases when the cyclone comes on the continental shelf, on the width of the continental shelf. Okay, that's why we have to consider what is the continental shelf at each and every location, along the coast. Okay, why it is increases? That's somebody can ask actually why over the continental shelf increases the the height of the surge, storm surge. Because as I said, storm surge is a long wave. It is the property of a long wave. When a long wave propagates from deep waters to shallow waters, okay, the width of the long wave decreases and wave height increases. That is the typical property of a long wave. Therefore, if a cyclone crosses on a wider shelf, then you can expect that the wavelength decreases and the wave height increases. Okay, the wave height is nothing but storm surge. Therefore, if you have a very long continental shelf, then you expect the amplification of the surge also increases quite a lot. That's very important. Okay, so I just want to show you. How much continental shelf width actually along the east coast. Okay, but here in the east coast, it's about 45 kilometers roughly on an average, up to even Odisha. Okay, you have a coast. The shelf width is about 50 kilometers. But if you go to Head Bay region, where Sundarbans, you have Hooghly region, Ganga, Brahmaputra. Of course, this is all in Bangladesh, wherever it is. But you have a very long continental shelf width. That means the waters are very, very shallow here. Okay, so you expect if a cyclone crosses here, if a cyclone crosses here, of the same intensity, you can get actually more storm surges here compared to here. Okay, because the width of the continental shelf is larger. That is the reason, basic. Okay, because the amplification takes place much higher. Not only storm surges, even tides also. The tides here are very large compared to this side. Okay. Similarly, tsunamis, that is also, tide is also a long wave. Tsunamis is also a long wave. Therefore, all long waves, generally, they increase its amplitude when they reach actually on a longer shelf widths. That's very, very important to understand. Okay. Therefore, we have to, what I am saying is that for any numerical model which we want to develop, you have to precisely see that whether the continental shelf width is properly, mentioned or not in the model. That's very important. Okay, so if you look at west coast of India, this is a very interesting, is that because the continental shelf width from 60, from here it is about 35-40 kilometers to 60 kilometers north of Kochi, and then it increases to 90 kilometers around that Mangalore and that region, and it increases continuously up to 300 kilometers, 330 kilometers, near Bombay highway and all those regions. Okay, Maharashtra region and Gujarat, all these areas have very long continental shelf width. So it means that any cyclone which crosses in this region, you expect larger storm surges. That means higher amplitudes of storm surges. That's very, very important. It is only based on only one parameter I am just talking about, shelf width. Okay, how the shelf width changes and how it converts into amplification. That's very important. But there are many other factors also. Okay, so this is a typical wind pattern in any cyclone. Okay, suppose this is the track of the cyclone. Let us. This is a very idealized situation. It's a pictorial representation of cyclonic winds in any cyclone. Suppose you have this is the coastline. Okay, this red line is the coastline, and the black line is the track of the cyclone. Then you always get actually, two kinds of winds. On the right side, you have onshore winds. On the left side, you have offshore winds. Okay. What is onshore winds? The winds which are actually blowing towards the coast. That is called onshore winds. Okay. The winds on the left side of the track, they are actually blowing off from the coast, blowing off the coast. That means the winds are actually away from the coast actually. Okay, but both are important because the winds which are on the right hand side, okay, that means the waters, these winds, okay, because of momentum and all these acting on the surface of the ocean, they carry the lot of water mass towards the coast actually. Okay, so that will pile up the water at the coast. That will pile up at the coast. That is called actually storm surge. Actually, storm surge by default, it is a positive storm surge. Okay, that means the water piling up at the coast is called positive storm surge. But at the same time, on the left hand side, the waters are actually taking away the water mass from the beach. Okay, so that means your beach is exposed on the left hand side. Okay, here there is a water piling, and here the water is taken away from the coast. So both are important. That means at the beach, the water is taken away. That means negative surge. This is called negative surge on the left side. On the other side, positive surge. But positive surge we always consider because it is actually, the surge which is developed at the coast will again penetrate over the land. That you call it actually inundation, coastal inundation due to storm surges. This is very well known. That means the coastal inhabitants are actually affected by this positive surge. But at the same time, this is all dangerous. This is very dangerous because you need to evacuate the local population whenever there is a positive surge. But at the same time, this negative surge is also important for the naval navigation, because if there is any ship here anchored here, that will be grounded. So therefore, it is equally important. It is equally important, negative surge also. Okay, as compared to positive surge, of course, it may not be that dangerous, but it is required for the naval operations and all. Actually, it's important. Negative surge also. Okay, yeah, this positive surge, which is actually accumulated over the coastline, okay, that will actually, they will not just stand there itself. It will propagate over the nearby land. Okay, it depends upon the, what is the land topography. Okay, it depends on the land topography. The storm surge accumulated near the coast will propagate inside. Okay, so how far it inundates, it depends upon the local topography. These things I would like to discuss later. But this is a typical pictorial representation of the wind system, which causes actually both positive surge on the right side and the negative surge on the left side. But as you go away from this landfall, the winds decrease. The winds decrease. Therefore, you may not get actually, storm surges very far off from the landfall point. You always get actually the storm surges within the radius of maximum winds. Okay. After that, there is a decrease in the storm surge generation and all these things. Okay, so this is again a kind of pictorial representation. Okay, as I said, there is a storm surge generated by the cyclonic winds, but on the top of it, you have a tide also. You have a tide. Okay, the tide is a continuous phenomenon. It's a regular phenomenon. You all know that one. There is a high tide. There is a low tide. Depends upon the periodic oscillations of the sea level rise is there. These are called actually astronomical tides. Okay, I don't want to go into the details of how the astronomical tides are this one, but every day you have two highs and two lows if it is a semi-diurnal tide. If it is a diurnal tide, there is a one peak every day. Suppose a cyclone crosses at the time of high tide, that means you have to add the tide also on the total water elevation. Okay, suppose in this figure, for example, there is a 15 feet surge is developed, generated by a cyclone, and already there is a 2 feet high tide, then that means total water level is about 17 feet storm tide. Actually, storm surge plus tide is called storm tide. That's my notation here. Okay, if I say storm tide, that means tide is also taken into account. Suppose if it is a low tide, at the time of cyclone landfall, then you expect the total water elevation will be less than what it is. Okay? Therefore, important is that you have to know what is the phase of the tide at the time of landfall. Very important. Okay, if you know the phase of the tide, then you can see that how the surge and the tide is interacting. Okay, this is very important. This is called tide surge interaction. Okay, so and also this damage due to any cyclone depends upon whether it is a highly elevated area or low elevated area. Okay, is it a low-lying area or highly elevated area? That's what I mean. Okay, if it is a highly elevated area like Visakhapatnam, let us say, because the land topography is a little high. Suppose a cyclone crosses near that, you can't expect that storm surge, even though the storm surge is generated about 2 meters, 3 meters, may not cause any inundation. Okay, but if it is a low-lying area, even 2 meters or 3 meters may cause a lot of inundation if it is a low-lying area. For example, there are so many low-lying areas along the east coast, along the west coast, particularly in the Bangladesh region, everything is low-lying area. Okay, so for them, even 1 meter storm surge is also, it will actually inundate much larger distances inside. Okay, even 2 meters means it may go up to longer distances inside. So therefore, it all depends upon where it is crossing, what is the land topography. That's very important. Okay, now let us come back to what is the storm surge. How do you define storm surge? A storm surge is, as I said, actually it's a wave, particularly a long wave. But you can always define the storm surge. It is an abnormal rise of sea level. Why I am saying abnormal? It is not a regular sea level rise like tides. Okay, another kind of rise of the sea level if it is a periodic, but this is not like that. It is an abnormal rise of sea level caused by cyclonic wind stress moving over a continental shelf. This is the definition of a storm surge. Okay, so what is the storm surge is the most destructive element associated with any tropical cyclone. If the storm surge is more, then you can say that destruction associated with that one is larger. Okay, so therefore you have to see prediction of storm surge is very, very important. Not only prediction of storm surge, but what we need for the public is that whether that storm surge is dangerous or not dangerous. That means whether it will cause any coastal inundation or not. How many people have to be evacuated because of this inundation? All these things are associated with the storm surge development. Therefore, the storm surge doesn't mean that it is always dangerous. Okay, as I said, if it is a highly elevated area, as I said, it's not a dangerous thing. So therefore, this dangerous or not dangerous depends upon the place where you are looking at, and you have to look at the land topography at that particular place. Okay, these are all actually very important parameters associated with any prediction system. Okay, so now I have just listed out some of the factors responsible for generation of storm surges. First, as I said, intensity of the cyclone. As I said earlier also, if the cyclone is more intense in terms of pressure drop, okay, then you can say that it is actually more vulnerable. Okay, another one is shallow bathymetry. If the cyclone passes through a deep waters, okay, it doesn't cause much waves created. Okay, there are long waves, but it's not that harmful. But if it is in particularly in shallow waters, the waves which are generated are larger. Similarly, continental shelf width, I already explained, and coastal line geometry and shape of the basin. Okay, because our coastline is not like a straight line. There are geometry of the coastline is changing drastically from place to place. At some places you have a concave shape, in some places you have a convex shape. So what kind of coastal geometry you have in a particular region is very, very important. If it is a concave, okay, then that means most of the energy is trapped in that one. Okay, if it is a convex type, then the energy dissipation is large. So it all depends actually. I will show you some of the shape of the basins where the energy, when the cyclone crosses in that particular, for example, Machilipatnam, okay, area, you can see the crescent shape of the coast. Okay, there when a cyclone crosses in that region, the energy gets trapped. So therefore, you expect more storm surges in that shape of the basin. Okay. Another important thing is approach angle of the tropical cyclone. Okay, most of the cyclones are crossing from south to north, actually, in that direction. But still, there are some cyclones which will take a U-turn and then make from north to south also. There are some cases. But what I am saying is that what is the angle of the cyclone with reference to the coastline? That's very important. That angle also makes a lot of difference because your onshore winds, offshore winds angle also changes because of that. Okay. Another one is that shape of the ocean basin. What is the shape of, for example, Bay of Bengal? It's a typical basin. It's a funneling shape of the basin. It is a funneling shape. Why I'm saying is that as you go from south to north in the Bay of Bengal, the width of the Bay of Bengal decreases. The width of the Bay of Bengal decreases from south to north. This is called funneling shape of the basin. So this is very important. Whenever there is a cyclone from Andaman's region, that is the generation side from where actually it propagates towards north. That means your energy is getting trapped actually in the funneling shape of the basin. Therefore, you expect that more storm surges in this shape of the basin. Okay, these are the generation of the storm surge. On the top of it, there are actually, the total water elevation caused by other factors. Okay, storm surge is one of the factor, and another factors are is the astronomical tides. Astronomical tides means it's a tides, as I said, it's a regular phenomenon. So therefore, you get actually interaction with the tides and storm surges that produces the total water elevation more or less. Actually, depends upon the phase of the tide. Another important thing is wind waves. Wind waves are also wind waves are actually short waves. As I said, the wave heights are very, very large compared to the wavelength. But these waves, when they break, they will create a lot of momentum on the surface of the ocean that will add actually, additional force to the, to the system. Therefore, this gives actually wave setup also. I don't want to go into the much details as due to that shortage of time, but wind waves are also very important. It will add additional momentum to the equations, to the system, total system, to contribute for the total water elevations. So now what you understood is that total water elevation is the most important thing, not only just storm surges, but you have to consider how the storm surges is being interacted with the tides and also wind waves. Okay, the total, the interaction is actually precisely contributes for the total water elevation. That means it has got so many components, total water elevation, because it doesn't matter what is the storm surge, what is this one for inundation. Total water elevation is more means you have more inundation. Depends upon the land topography. That's what you have to understand. So factors responsible for coastal inundation. Okay, once you have a total elevation, then the next important for any model to see that how much coastal inundation takes place at that region, in that region. Okay, one is local land topography. This is very, very important. Land topography. Okay, that means what are the height of the topography, and not only that. Actually, I forgot to mention here LULC, land use, land cover. Okay, that is also very important. Suppose you have mangroves more. Okay, for example, in the Sundarbans, there are many mangrove systems. Okay, that will prevent actually coastal inundation also. So you need to have more mangrove systems along the coast so that you can arrest the propagation of the total water elevation inside the land. So that will be also very important. And also particularly when a cyclone lands in the near basin, river basin, for example, Mahanadi. We have so many river systems along the east coast. Mahanadi, of course, Hooghly, Ganga, Brahmaputra, all those things. After that, you have Mahanadi, Krishna, Godavari, and all these river basins, are very important actually when the cyclone lands in that one, because the water propagates to the river much interior and it can inundate larger areas nearby. Okay, now this is all about very introduction part. I said now I would like to say that some of my work actually done how much because this gives actually what kind of probable extreme water elevations associated in due to tropical cyclones along the Indian coast. In fact, I considered both east coast and west coast. We studied very in detail how much extreme water levels could happen. Probable extreme waters. Probable means it's not on real time. Okay, we do whatever the models we developed at our center. We already gave it to transferred our technology to India Meteorological Department for their operational use. So therefore, I'm not presenting any how the models are actually performing. It's performing. I know it gives not only total water elevation and also associated inundation also it gives. So, but what I would like to present here is that considering the vast stretch of coastline, where are the pockets where you get mostly, extreme water elevations and how much inundation takes place in each district wise? That's what I'm going to present. So for this, to make the long story short, I have considered a lot of data for the last 125 years. India Meteorological Department data is of cyclone tracks and its intensity is considered. Okay, you have the data, so you can always reorganize the data on a district level. Okay, and if you know for in a particular district, this many number of cyclones are occurring in over a period of 125 years, you can construct a synthetic track based on that real tracks. Okay, there is a way of constructing the synthetic tracks. Okay, for each district, I constructed a synthetic track along the east coast. I'm showing similar. I did actually for the west coast also, and again we also observed what is the pressure drop what is the pressure drop in the on a 100-year return period? What is the pressure drop for each maritime state? For example, West Bengal 75 millibar, Odisha 98, Andhra Pradesh 82, Tamil Nadu 66. Okay, so we have actually taken the pressure drop maximum because I want to see the maximum probable water levels, total water levels rather. Uh, and also I considered, synthetic tracks. For West Bengal coastline, there are only 2 synthetic tracks. And for Tamil Nadu, we have long coastline, so 13 tracks. For Andhra Pradesh, it is 8. Like that, we have taken the number of synthetic tracks also for each maritime state. And I ran our model, numerical model, right? And also I assumed that at the time of high tide, okay, where you get actually maximum extreme water levels, water elevations rather. Okay, so therefore I have taken at a high tide how much it could contribute, how much it contributes actually the total water elevation. That is the question. Okay, I addressed that one. And I also actually considered on the global warming scenario. The global warming scenario, there is a IPCC report that says that the strength of the intensity of the cyclone increases from 2 to 11%. So therefore, I considered that IPCC report and I increased the intensity of the cyclone by 7% and 11% for moderate and extreme case of warming scenario. So I considered those climate scenarios also to see how much this coastline is being affected. These are the, objective of my presentation for the few minutes more. Okay, so and also I considered all the river systems, Hooghly region, okay, and Mahanadi basin, and you have Godavari, Krishna. I have already taken these river systems also in the model, okay, and the details of the river systems are given here, and depth of the this is actually bathymetry, topography, this is topography. Topography means on the land. Okay, this is the depth actually, this is the land topography, because land topography is very important for the inundation, for calculating the inundation. So I don't want to go into the details, but we have taken the SRTM data and we have land topography data. And also these are the river systems which are considered. Okay, so the model considers, all the features because that's very important to calculate more accurately. As much, accuracy you need is very important. You need very accurate land topography and all that. Whatever is the best available data we have taken for calculation. This one, that is the background for these models. Okay, so now I'm bringing actually what is the probable maximum elevations, water elevations rather. Okay, so for Odisha, West Bengal, and Andhra Pradesh, Tamil Nadu. Okay, but if you look at for the entire Odisha, for example, okay, everywhere you are not getting maximum water levels. Only in some pockets. In some pockets, for example, Badrak, Dhamra, Badrak, and Balasur. See, in this pocket, you have a lot of, surge development. First, I will explain the surge development. So you get about 9 to 10 meters surges here. Okay, because of this one, the area gets inundated. Okay, area of inundation doesn't, if you have higher surges, it doesn't mean that you will get larger areas of inundation. It all depends upon, again, what is the land topography. But here, you have more inundation in the, there is a river system here. There is a river system here, Mahanadi river system. Okay, so because of low-lying area, you get a lot of inundation here. So I have shown actually which are the pockets where you get storm surges more and where you get more inundation. This is the extent of inundation. This gives the extent of inundation. So, and also what is the water level in that extension? Is it 2 meter level water inundation or 3 meter? Because that is all very important actually, because for evacuation of the local population. Okay, so this information is being done at each district level for the East Coast. Okay, you can see actual details. If anybody is interested, one can see our papers published in this region. Okay, more discussion is done in that one. Similarly, for the West Coast, you have 24 paragraphs, and all these are very important for the inundation point of view, because these are all low-lying areas. Okay, so therefore you get more easterly inundation here also. In Andhra Pradesh, wherever you have the river basins, it is obviously expected that you have more inundation. Very important here. Okay, you have more inundation here. Similarly, Tamil Nadu, you have a very important that you have in this region. Okay, you have more in storm surges and inundation compared to other parts of this one. I don't mean that there are other parts are not important. I'm saying that what is the most vulnerable areas and what are the most vulnerable areas for the inundation purpose as well as storm surge purpose. Okay. It may not coincide exactly. The storm surges may be more high, but you may not get inundation more high because it depends upon the land topography. That distinction you have to make it. Okay, I'm just showing that I'm just showing actually, district wise. This is district wide. We have got so many districts. Each marine state has got so many districts. So I'm putting actually on each district what is the normal present how it is producing actually maximum water elevations. This includes tide also. Okay, so therefore these are the, and also how much inundated area for each district. Okay, very important. You can see that Mandipur and 24 Parganas actually having larger inundated area compared to any other region. Okay, so you can see that how much area is getting inundated for each district, and what is the storm surge at that place, and how much inundated area for, if it is less than 1 meter, if it is more than 1 meter to 2 meters area, greater than 2 meters. Okay, why I am putting this distinction is that anything more than 2 meters is most dangerous, because the local population have to be evacuated. Very important. If it is less than 1 meter, people, they are not at that risk. Therefore, if the area is more than 2 meters, that area, area's population are to be evacuated. So for this purpose, so okay, I made actually distinction between different levels of water levels in the inundated levels rather. Okay, for each district. Okay, so again, coming back to climate scenario, okay, so I have projected actually in the moderate climate scenario and extreme climate scenario, okay, by raising the wind stress, okay, rather winds, cyclonic winds by 7% and 11%, okay. Then in a climate scenario, how the each coastline, how the each coastal district is being affected. I don't want to go into the details, but very important thing, there are some districts actually more vulnerable in the climate, in the warming scenario. Okay, you can see these results more carefully and analyze. Okay, one can do that one. Okay, so similarly on the west coast, okay, I did only for Gujarat and Maharashtra, presuming that Kerala and Karnataka are not that much this one. So I calculated only for Gujarat. You can see that actually in Gujarat, there are some pockets, Gulf of Khambat and Gulf of Kutch, where you expect the tides are very, very large. Therefore, the total water elevations can reach up to 10 meters, 11 meters. So very important actually in that region. But Maharashtra is not that much, it will go up to 4 to 5 meters. So therefore, in the if there is no climate change, I have already shown, and this is all actually calculated on the basis of 100-year return period. Okay, so therefore, I have seen actually what could be the maximum possible, probable maximum water elevations. That's all we have projecting here. Okay, so. Okay, so in a climate change, okay, or in a 100 return period, so in each maritime state, how it is being affected, that's very important actually, if you see Kerala, I will show you later actually, Kerala is actually being mostly affected by the climate warming scenario, extreme warming scenario. Okay, because you can see that 15.8% and 31.6 compared to other this one. This state, Kerala is also, Kerala is, as of now, we are not considering is a cyclonic area. Okay, but in the extreme climate scenario, Kerala is going to be, very, it is having actually threat from the cyclones also in future, if the IPCC reports are all correct. Okay, you can see from this is the normal scenario at yeah, right, and this is actually 50-year scenario, and this is 100-year scenario. This is the moderate normal scenario. This is again 50-year return period. This is 100 years return period. This similarly for 100-year return period. But if you see this one, you can see that the southern part of West Coast is also, and the southern part of Tamil Nadu and all, they become actually extremely, extremely, serious situation in the as per the IPCC reports. It's all going to be very, very vulnerable actually in terms of generation of some storm surges and associated inundation for this region. But in the normal case, as of now, we don't. This is the case where it is at present. Okay, we don't have any much danger actually for these regions. But in the climate scenario, the last scenario, there are 9 scenarios I have generated. In the last scenario is the worst part of it. Okay, and this is the present actually. So from present to climate scenario, how the situation is changing drastically, one could see that one. Okay, so this is actually Gulf of Khambat. Gulf of Khambat is also going to be very serious issue in the global warming scenario. So you can see that how it is dangerous in the worst scenario. Okay, so I would like to spend another 15 minutes left actually for you. This another important factor is that if a cyclone, um, lands actually in the Mahanadi Basin or any river system. I am talking about Hooghly Basin, Krishna or Godavari, anywhere. Okay, but there actually you need actually a kind of different model. You can't use the same model actually. You need because it's a river system. You need to know actually what is the hydrological part of the system also. Okay, because any cyclone is associated with a lot of precipitation. Okay, if it particularly in the river system, okay, so lot of if there is a lot of precipitation, you expect that that area is low-lying area, so therefore you expect actually more inundation. Okay, and you have river systems which bring a lot of fresh water from the upstream end of the river, so that will also bring a lot of river runoff, and from the seaside there is a storm surge. From the upstream end, there is a fresh water. Okay, because of the lot of rain over the river basin, also there is a lot of precipitation because of the cyclone. So combining all these things, okay, you expect that it is more vulnerable more vulnerable situation. Therefore, in this region, you need to have a separate model. You need to have a coupled system. Okay, it is just the model which we are using at CIRC. Okay, advanced circulation model is not sufficient enough to take care of particularly in the river systems. Okay, so for this we need to have a river model. Basically, all river models are actually hydrological models. Okay, that means it simulates actually the flow conditions in the river channels. Okay, in the floodplains and all. Therefore, we use actually HECROS model, which is developed by US Army. Actually, they use actually this HECROS model also for their operational purpose for any kind of river flow, river flooding and all those things. But I used that model and I coupled with the model which I already using, that is called XCIRC. And that means I have to see that in forces coming from the storm surges, and also as a result of river discharge from the upstream end of the river plus precipitation, all these things I have to incorporate in this coupled model. So which I did it. So I will just show some of the results. Actually, a lot of work is there actually, but I don't want to go into the details of this work. But I considered 2 cyclones. One in the 1999 super cyclone, you all remember probably. This was the most vulnerable cyclone which crossed actually along the east coast. That actually killed many people also in this region. And 2013, there is a Phylon cyclone that is given by this one. This is I have taken two cyclones specifically. One cyclone is crossing in the Mahanadi Basin, exactly in the Mahanadi Basin. The landfall point is in the Mahanadi Basin, but this Phylline cyclone is south of this one. Okay, so I considered these two tracks for some reasons to see that how the within the basin and away from the basin, how it makes the difference. That's the idea of taking these two cyclones. Okay, so for these cyclones, I have considered actually I have considered the precipitation also. You can see that how much amount of precipitation. I have considered a daily precipitation, area average also, but one can take actually grid point data also, because at that time when the paper was published, we could not do that grid data, but we used actually area average data. You can see compared to Phylline cyclone, this super cyclone precipitated heavily, 21 centimeters, 25 centimeters, 7 centimeters, all the compared to this Phylline cyclone. So therefore, you can include this precipitation also. This is the first time that we did actually inclusion of precipitation and river discharge from the upstream. No model so far was there before that actually to incorporate. Storm surge was calculated, tides we have taken, wind waves we have taken, but nobody has taken this precipitation and river discharge. So we have taken and published in JGR Oceans. Okay, so I may not go through too much of technical things, because what is important is that how important to represent the river system more accurately. That's very important. This Mahanadi Basin particularly has got Baitarani, Brahmani, Mahanadi, three tributaries. Okay, these tributaries are very, very important. So we have to consider actually, cross sections of these tributaries more accurately. So we have got data from the CWC, Central Water Commission. So we have idealized these tributaries very more or less accurately using their data. So try to represent the Mahanadi Basin more accurately. And try to incorporate all the tributaries. Okay, I don't want to go. So you look at the cross sections also. We have taken the cross sections also. Very laborious work actually, this one. Okay, at each and every tributary we have taken so many points. What is the cross section? Because the cross section is more important to hold the water. Okay, total water in terms of volumes actually. Okay, after that only it overflows. Then only you will get actually the inundation over the banks. Okay, so all these things are very important. I don't want to go into the details, but we used actually SRTM data. But I hope you all know that SRTM data, it is a shuttle radar topography mission, which gives very high resolution data. But this is not sufficient enough to represent the tributaries more accurately. So we have to modify the SRTM data based on the real ground truth data. So we did all those things and we used the correct river tributary data. Okay, and this is the discharge also. We got the data. So we have each basin, each tributary, how much discharge meter cube per second is coming. So that is the force also coming from the north of the upstream end of the river. So we have seen actually contribution of each tributary, and Brahmani is contributing a lot. I don't want to go into the details, but eventually we have taken LULC also, land use, land cover. What is the in this region? What is the land cover, particularly agricultural land, or is there any wetlands? All those the information is already taken into this system also. So you have to consider LULC also in order to give the more accurate representation of the inundation. So therefore, we have seen with LULC, without LULC, what makes the difference and all those things. But we found that LULC representation gives more or less accurate way of prediction of the inundation. Okay, so I don't want to go into the details of this one again. Okay, so what is important is that if you consider inundation without, if you don't consider precipitation and without precipitation, it makes a lot of difference. We have seen that, I don't know how many people you know, in 1999 that super cyclone was sitting over the Mahanadi basin for 2 days and pouring a lot of precipitation. Okay. Because of that one, the inundated area is very, very large. So that's what exactly the model also reproduces. If you don't consider precipitation of the cycle during the cyclone time, the inundation levels are different, very less actually. On the left side without precipitation, on the right side you have a precipitation included. So that makes a lot of difference in the inundation levels also. These are all inundated area, the green ones, green and this color. Okay. And also maximum water levels are also given. What is the water level, depth of the water level? Okay. Okay. This is another experiment, but we have done actually with the Phylline cyclone also. In Phylline cyclone, we got the satellite Landsat data. Okay. Just before the this one cyclone is like this, and after the cyclone, of course, actually this satellite data we got after 1 week of the cyclone landfall. So therefore, more or less we are getting, you see this patch, for example, this is the inundated area shown in the Landsat satellite picture, but this is the area is exactly matching in our model also. Okay. So this is during the 2015 Phylline cyclone. So we have compared with the satellite data also. So what I am just showing is that how you can validate. Basically, inundation is a very tricky business. You cannot compare with the ground truth data also, because it doesn't give the depth of the water levels, but it gives the spread through satellite. Okay. What I'm coming back, what is this is the type of work done first time for our region, including the precipitation and also upstream river discharge and the calculation of inundation based on this one through a coupled model. So we have coupled actually a hydrological model with the hydrodynamic model and get the realistic situation of flooding. Okay. And finally, what you need is that you need a location-specific integrated prediction system for the assessment of cyclonic risk and vulnerability. Risk means actually how much it causes the damage, whether it is actually very high level dangerous such or not. That's all the risk actually, and the vulnerability, because of that one, how much area is going to be inundated, how actually what are the areas to be evacuated. All these things actually you need such kind of an integrated model. For this you need first of all your cyclonic winds data should be very accurate. That means in terms of your input coming from the mesoscale atmospheric model for any cyclone, you can get that one. If the cyclone prediction is correct, then your storm surge prediction is also correct, because they have all the input coming from the atmospheric model. But as of now, there is no atmospheric model which predicts more accurately the landfall and its intensity of the cyclone. So therefore, what we are doing in absence of this one, we are using actually kind of to derive distribution of the wind system is done by the parametric models. Okay, right now we are not using any atmospheric model. Still, it is in the R&D mode. Okay, computation of storm tides. We are doing this one very, tides are the very accurate, one can do accurate predictions for tides. So tide surge interaction is not an issue. And also the wind waves also is not a problem. So we have a very good wave models. We have coupled all these models actually. So that is not an issue. Okay, computation of coastal inundation using a coupled hydraulic and hydrodynamic models. This is also we have carried out recently. One of my students actually, got her PhD in this one, coupled models. Another important is that you have to incorporate all these coupled inundation models with the GIS themes, so that you can actually specific location site specifications can be identified for the vulnerability. And also, finally, what is important is for the stakeholders, state and central stakeholders, is that you have to identify the vulnerability to the affected areas of the cyclone. This is the most important thing. So for this, you need actually a lot of data. Very high resolution cyclonic winds are required. that is not even possible through satellites also nowadays. Okay, we need actually much more high resolution than what we are getting at this moment through satellite also. Okay, so also actually temporal resolution is also very important. As of now, we get about 6 hourly or 3 hours maximum, but we need actually at least half an hour interval. Satellite means then you can have good predictions actually. Another important thing is accurate bathymetry. As I told you, bathymetry plays an important role, but particularly over the continental shelf. And another one is detailed coastal geometry, including the river basin. Okay, this is very important data which is required for the inundation. And also we need the land topography more accurately. SRTM, we are actually merging all the satellite products, SRTM, ALTM, all this with LULC. All these things we are merging actually to get more and more accurate prediction of coastal inundation.